So in this clip, we have a result that guarantees for us when we have existence of eigenvalues. And so in particular, this is for a finite dimensional complex vector space. So let V be a finite dimensional complex vector space. Okay, so we'll take the dimension of V to be n, and we also want to rule out the trivial vector space. Okay, so V is a non-trivial finite dimensional complex vector space. All right. Then every operator on V has at least one eigenvalue. Okay, and so we've seen examples that indicate why these hypotheses are necessary. So for the infinite dimensional part, if you remember the shift operator example on the sequence space, and then that the complex part is necessary, recall the example of rotation on R2, where there was no eigenvalue. So those hypotheses are definitely needed. Okay, let's go ahead and prove this bad boy. If we look at any non-zero vector in V, then the list V, TV, T squared, V, so we just start with a vector and then apply the transform to it again and again and again and see where it goes. And this is the basis of the study of dynamical systems, which is a fun thing that we don't get to talk about. By the time you get up to T and V, then there are going to be n plus 1 vectors in this list, and we have a theorem that tells us that this has to be dependent because we're in a space of dimension n. And that one is 223. Okay, so then by 221, we can figure out when the first time is that one of these vectors is going to be in the span of the others. So let's let M be the point where we can solve A0V plus A1 T1V plus A2 T squared V plus up to AMTMV being equal to 0. So that's our first dependence relation. And at least one of those AKs needs to be non-zero. Okay, then let's consider the polynomial. So we know that the corresponding polynomial here, A0 plus A1Z plus A2Z squared, etc. This guy is going to be, actually, you know what? Let me back up. Sorry, minor typo. Let me call these guys AN, TN, and Z to the N. And then we can factor this guy by the fundamental theorem of algebra. And then here we get, we might have that m is not equal to n if an is equal to 0 in this dependence relation right here. Okay, so then let's see. So if we look at the sum k equals 1 up to m of ak, tk, v, then this is going to be the same thing as the polynomial applied to t applied to v. And so that's just like, you can imagine factoring the v out of this expression by putting parentheses right here. And then this factors based on what we just wrote. T minus lambda 1i, t minus lambda 2i, t minus lambda mi applied to v still. And from our equation above, when we apply this polynomial in t to v, we get 0, right? So that's just from this part here. Okay, now looking at this expression that we've just written down, we have to have that one of these has to fail injectivity. And then that means that TV is going to equal to lambda jv for that j. And we have an eigenvalue.